Okay, I want to go over a Python implementation of training a linear perceptron to model a Boolean gate. So this is the Jupyter notebook that you're gonna find under Canvas. You see that the first part, I define the data, which consists of a pair of inputs, x1 and x2, and the correspondent label, y. And you can see here, for example, now if you want to model the OR gate, so we have that, these are all the possible inputs. There are four pairs. And, when the input is false and false, the output is also false. And here now I also wrote the data for the other Boolean gates, the AND gate, the negation of AND, the not AND, and the XOR gate. The XOR gate, it is similar to the OR gate, but either of them can win, but we can only have one winner, but we cannot have two winners. And so what happened is that, when the inputs are both 1 and 1, the output will be false. Otherwise, in the other cases, when there is one of the two can win, it's gonna happen. So we have 1 and 1, and similar for the other Boolean gates. So as you know, with the linear perceptron, we need to, in order to train the perceptron, we need to estimate weights, which in this case, is there are two values, one W1 and W2, and a bias, which is basically a scalar. And this will be done in the training algorithm. We define the learning rate, and then the number of iterations of epochs that we want to do in order to attain convergence. And we're gonna, we're gonna do a gradient descent algorithm minimizing an energy, and which is also the loss function. And initially, we set an empty value because here we're gonna store all the energy or loss function values over the number of epochs. And so what you do first, you have the training loop is very easy. So we first iterate over the epochs in the range from 1 to 30. And then, we swap over all the data set, which are 4 pairs. And so, here we have the input pairs, x1 and x2, and the corresponding labels or outputs. And the first things we do now, we basically, let me make it smaller so that we first compute the dot product of the weights dotted with the data plus the bias. And then we say, we apply the sign function, the activation function. If this quantity, it is positive, we assign value 1, otherwise -1. And then that's where the computation, the updates of the weights happen. If the product between the predicted output and the target output from the data, it is negative, it means that we have a mismatch. So we have a misclassification of the I data label with I. And what is the error? The error, we measure the error with minus the product between yi, the target output, and the argument of the perceptron. Because if this product is negative, it means that we are misclassifying the data. And so with the minus in front of it, we get a positive error. So the goal basically, is we want this quantity to be, this basically give me a positive error. And then the corrections of the weights and bias are done based on the gradient descent and that I cover in the previous video for this course. So you see the weights, which are a vector, they are updated, by multiplying the output times the data input, the input data, and which is a vector, which have the same side, and the bias is a real number, which is just updated. And this is done, the correction of the weights and bias is only done when we misclassify one given data point. Otherwise, we don't do anything, and this is repeated until eventually this error goes to 0. Once we classify all the data correctly, what happens is that this error will become 0 eventually. And then I plot the loss function as a function, or the energy as a function of the epochs, just to get an idea how fast or slow is the convergence. And then we test the perceptron. So here we have a function that we put it does a loop over the pairs of data, the input data and the corresponding label or output. And here this is the two vectors and list of outputs. They are zipped together to form basically a pair of variables. One a vector, the one is a list and a number. And then basically, we apply the perceptron rule. We first compute the dot product, W times X plus the bias, and then we apply the activation function to see what is the predicted output, which is then, is plotted, input, output, and then the predicted output. And if we train the perceptron correctly, we should get a match here. And then, for clarity, I also do a plotting of the data points in the input space, x1 and x2. And so this is basically, all the Python code, to do that. And I also plot the decision boundary line, which, it is basically this equation equal to 0, because now we train the weights, we know what are the weights and the bias. And in order to plot this line, you see that I write x2 equal to minus the weight w1 divided w2 and so on. So remember that Python number the indices from 0. And so basically, this weight. So what we have here, we have the formula x2 equal minus w1 times x1 plus b divided by w2. This is basically w2. And as you can see, this is basically, an alternative way, to write this equation. Okay. And now let's run it. So and let's see what let's see what happened. So you see that initially, we started with random weights and bias, and the end error is pretty large. And then, as in the loop, we are misclassifying data points. There is a correction of the weights, And you see that the convergence is very fast. Already after 3 epochs, we basically classify all the 3 data correctly. And so, we didn't need to put 30 epochs, but, in this case, it converged very fast. And here you can see the testing. So we put this input, these 4 inputs. These are the target output. That's what we expect to be the output. And these are the predicted output. You see that, they match the expected output. And here there is a plot of the input space. These are the 3 inputs that give positive, false, true outputs, and this is the negative one. You see that we can clearly classify the data by drawing a decision line which separate -1 output for +1 outputs. And of course, this line, it is not unique. For example, if we rerun the code, remember that the code initially it has random weights. If we redo it again, you see that because the initial conditions are different. Now it took a little bit longer for the perceptron for the algorithm to converge, but we got convergence in 9 iterations, and the prediction are still good. And you see that this is a different line than the one that we got before. And this, be careful that this is not going through the point, okay? So, and that's it.